Hey friends, Dr. Liberty here, and we are going to dive into some details on inorganic chemistry today. Again, I am using the OpenStax text, but you need to take this information and make sure that you're reviewing it in whatever text that you are using, even if it is not the OpenStax text. I'm going to share my screen with you, and we are going to take a look at this. This just keeps me on track, gives me some of the things to make sure that I go over with you. So we're just in the textbook. We want to talk about inorganic chemistry. So we need to make sure that we discuss what makes something organic versus inorganic. So in the chemistry world, again, I think when people hear organic, the first thing they think about is food and the grocery store, maybe the vegetable and fruit section. And while I tell you, no, we're not talking about food, food is the easiest way to remember what is organic and not. So organic compounds are defined chemically by having both carbon, C, and hydrogen, H. So something that does not have both C and H as their chemical makeup is automatically in the inorganic compound side of things, or the inorganic category. So most stuff is inorganic, but we're going to pick out a few things that are important to talk about here. Organic will be a separate video. We've already done an intro. There'll be a separate video going over some of the details with that. So the three categories of things that we're going to talk about, number one is water. Number two, salts, not salt like on your food exactly, but salts. And then number three, pH, acids and bases. All right, so number one, we're going to talk about water. So water is, what is the chemical formulation of water? It is H2O, meaning that we have two hydrogens and one oxygen. Do you hear C in that? You do not. So since we have hydrogen but no carbon, water is considered inorganic, okay? Why is water important in the body? Well, it has a few different features that are going to make it act a certain way within our bodies. First of all, it is a lubricant. So we have water that is in the fluid that is lubricating, and the primary place that we talk about this is in your joints. You also have water in the fluid between the lungs and the membrane outside the lungs. So as they rub past each other, they are gliding past each other, not actually physically rubbing. It's also a cushion. So when we think about like the brain in the skull, the cerebrospinal fluid has a lot of water in it, and that acts as a cushion. So if we hit our head, the brain has that water in between. It doesn't automatically smack into your skull. Baby, developing fetus, also again, fluid, water there as a cushion. So mom can move around, and baby's not gonna slam into the wall of the uterus because there's water, there's a fluid in there helping to cushion that. Number two, water as a heat sink. So this is kind of a chemistry thing, but the idea is that water does not change temperature very quickly. It can absorb heat, it can release heat, but it doesn't do it really fast. So if you go out into 120-degree air, you are not automatically going to heat up to 120 degrees. If you go out into -30-degree temperatures, you are not automatically going to lose all your heat. So water acts as a substance, and since we're 70-ish% water, water acts as a substance that can absorb or dissipate heat or hold on to heat as needed, but it's not going to do it instantaneously. It takes time for it to heat up and time for it to cool down, and that gives us a buffer to be in extreme temperatures without our core body temperature changing. It's also part of liquid mixtures, and so if you look down here, water is considered the universal solvent, and we need that solvent so that things can dissolve into it. So we don't have water running through our veins, we have blood that is going to start out with water and then have a lot of things added to it. So think about like sweet tea. You have the tea, you have the sugar, maybe you have some mint, you have things that you have dissolved into that water. So the water serves as kind of a carrier. So it's very important because things can dissolve and can interact with water, but still be their own thing. It makes it important for how water acts as a transport mechanism, how gases can dissolve into that water and travel to other places deep in the body that don't have access on the outside. or how our food items can go into that and then be transported. So it's important that we have the ability for things to dissolve in water, but also to enter and then maybe also exit without being changed or altered in that. So here we talk about concentration. So since we just brought up solutions, we're going to bring up a topic called osmosis. And we have to talk about concentration of solutes for this. So how did we get here? It's a really weird, like we were just talking about water, because water helps make solutions, because we have water and then we have stuff that goes into the water. So we have a variety of words that we're going to use when we talk about solutes. Let's talk first about these. When things are dissolved completely in the water, that is the solution. So here we have a solution. Liquid solution is a solvent, so water, that dissolves a substance called a solute. So again, sweet tea, we have the tea, let's say the sugar, that is completely dissolved. If I put up a pitcher of sweet tea and a pitcher of unsweet tea, if I put a pitcher of water that had sugar or salt or something completely dissolved in it, would you be able to tell the difference between that pitcher and a pitcher of water with nothing in it? If it's completely dissolved, the answer is no. There's nothing that would point to it being in there. So that's a solution. There's also something called a colloid. A colloid is still a solution. Something is still dissolved, meaning that it is equidistant from all the other molecules in it. Sorry, I don't know why it keeps popping up with links to my classes. But the colloid is something, it's a mixture of something that's actually bigger. So usually this is opaque. This is more like the tea, or this is more like your Kool-Aid. So if I have a pitcher of water and I have a pitcher, like a pitcher of Kool-Aid, can you tell the difference between those? Well, of course you can, right? Because you can see the color of the Kool-Aid. So those molecules are larger than the sugar. They don't dissolve, well, they spread out equally, they dissolve, but they're larger. And so they are opaque, or in that case, it has a color, and you can't see through it the same as you could see through salt water or sugar water, where it's completely dissolved. A suspension is where it's a temporary spreading out of the molecules. If we put sand into water and we shook it up, we would have sand distributed all through that pitcher of water or that bottle of water. But after a while, what would happen to the sand? It would settle out, right? So it's not actually dissolved. It's just kind of spreading out within the water space. So we don't want this to happen in the body, because what would happen if your blood, for instance, if the fluid part of your blood, if you started having heavy stuff that just kind of sank out of it, you know, it would sink to the bottom of the vessel. The vessel's running this way, it would sink to the bottom of the vessel. The vessel's going this way, it would sink to the bottom. That would be really weird. It wouldn't be able to circulate, it wouldn't be able to travel. So we don't want this to happen. We do see this happening in certain disease processes. There's something called the ESR, the erythrocyte sedimentation rate, and we want to see how quickly the red blood cells settle. If they settle too quickly, then we have a problem. They should remain kind of buoyant. It doesn't mean they float at the top, but they should remain kind of buoyant so that they can travel easily. When we have really high inflammation, the ESR, the sed rate, is going to go up. So that's not a great thing, but that is an example of the difference. That is a particle that is so large that it can't stay dissolved or spread equally throughout the solution or through the solvent. So why is water important? Well, we are going to talk about organic chemistry for a second. Water is what links, allows us to link together our organic monomers. So we take away, in dehydration synthesis, dehydrate. What are we doing if we dehydrate fruit or dehydrate meat? We're taking away the water. So dehydration, taking away water. Synthesis, if we synthesize something, we're putting something together. So put this all together, take away water, put together. What does that mean? It means when we want to put monomer 1 and monomer 2 and connect them together, we do that by taking off an H and an OH. So they have this little hydroxyl group sticking out, this little OH group sticking out, and it's like uncapping a pen, okay? So if I want to connect this, I have to uncap it. So now it has an open place so it can interact, right? If I want this to interact with my paper, I have to uncap the pen. Okay, I have to uncap the pen so it can interact with the paper. If I want monomer 1 and monomer 2 to connect together, we have to take off the H2O. So dehydration synthesis means that we end up with things that are stuck together because we took out a water. The opposite of that is true. Hydrolysis, hydro meaning water, lysis meaning break. We use the molecule of water to break the two things apart. We put that H2O back into the molecules, and instead of having two things that are connected, we've separated them out into two whole molecules. So you use these words. I know these are big sciencey words, but break it down. These are not hard words. This is not stuff that is new to you. You've heard of dehydration. You've heard hydro before. Use those things to make it make sense, okay? So why is water important? Why do you have to have a certain amount of water in your body? Because your very ability to break down the food that you eat and build it back up into the components of your body require water as part of those chemical reactions. So that's a really big deal, in addition to all the other features we've already talked about. Okay, so if you are still having trouble with anything to do with water topics or questions, make sure you email me and let me know. Let's switch over and talk about salts. So a salt in the chemical world is two ions that have formed an ionic bond. So we usually have a plus and a minus, or we have a 2 plus and a 2 minus, and they've linked together because chemically opposites attract. That plus and that minus, they fill out each other's valence, or they give up or they take electrons to fill out their valence shell. And then when they get into water, they let go of each other. So salt that you think of on the table is NaCl, sodium chloride. If we drop salt into water, it's going to dissociate. All of the sodium here and the chlorine here are going to let go of each other. Why? Because water is polar. Because water molecules have a positive end and a negative end, and they're going to line up around those ions to match. So sodium is a positive ion. It gave away an electron. And so the negative oxygen end is going to line up around this way. And all the negative sides, the little Mickey Mouse ear hydrogens, are going to be attracted. The positive sides, the hydrogen, is going to be attracted to the negative chlorine. So ions get along with water because water is polar. Water has poles. It has a sort of positive and a two sort of negative ends, and it likes to hang out with things that are charged because it can interact, right? It's like a magnet working with a refrigerator. I can't stick a magnet on the wall of my office because the magnet and the drywall aren't going to interact with each other. But if I stick a magnet on my refrigerator, it sticks, it interacts because it's magnetic and metal. Okay, so ions and water love each other. They play well together. Why does this matter? If you see salt, it means that there's something, there's an ion, there's something with a charge that is going to interact in a certain way. NaCl is important. There's lots of other chemicals that are salts, potassium chloride, magnesium hydroxide. There's a lot of things that are salts because they're ionic, and we need those as elements or as building blocks of other things in the body. All right, so salt. Want to make sure we define that, and we'll talk about it later. We'll bring it up. Like I said, it's calcium phosphate salts in the teeth and bones. So that'll come back in the bone chapter. Bile salts we'll talk about again in the digestive chapter. So you'll see that come back up. Okay, number 3, we're going to talk about pH. pH. Let's skip down here for a minute. pH is how acidic or how basic a solution is. We are looking at the amount of hydrogen. That capital H in pH is a measure, if you will, the amount of hydrogen ion concentration in a solution. So now let's back up. Okay, so an acid is a substance that releases hydrogen ions. Okay, an acid is something that releases hydrogen ion. A hydrogen ion is basically just a proton. If you go back to the periodic table, H number 1, so it has 1 proton, 1 electron. It gives away that electron, and it is just a proton running around. So H plus is literally just a proton. So if you see something that says proton donor or proton acceptor, that's referring to this. H plus is a proton. So strong acid, when it hits water, is going to completely dissociate because it's going to have an H plus and whatever the minus is. Hydrochloric acid, HCl, is a hydrogen attached to a chlorine. We just looked at chlorine here, right? Sodium chloride, same thing. HCl would just be a hydrogen attached to a chlorine. So a strong acid is one that when you drop it in water, it is going to completely separate, or ionize means it's going to separate out into its 2 ions. These are beneficial. We have mechanisms in place to protect our body from these kinds of things, like in the stomach, there's a lot of layers and mucus and stuff like that. But they are really important for, well, this is really important for the digestive process. By the way, acid does not do the digesting. Acid actually activates your protein enzymes. That is a big thing I have to fix for a lot of people. Acid doesn't do the digesting, but it does create the environment for digestion of proteins to occur. A base can be defined 2 ways. It either releases hydroxyl ions. So a hydroxyl ion is OH, and it's OH minus. So it's a negative ion, also called an anion. Remember that one? So it either releases OH, so it's the other side of water, right? H2O. So an H and an OH. See that? So a base either releases OH or it accepts hydrogen, okay? Or it accepts a hydrogen that's already present. So a base kind of has 2 potential chemical interactions that could occur. Could do just one or just the other. Yeah, so we talk a lot in the body about being able to remove hydrogen, remove those protons and accepting that, kind of getting it out of the way. So that we don't get too acidic, because too acidic, again, could cause tissue damage. We measure pH, again, by the hydrogen concentration of the solution. So H, the hydrogen, is the really important thing that we're listening to. It is also a base 10 logarithm, which means pH solution of pH 4 has 10 times more hydrogen than a solution with a pH of 5. So it's not a little change as we go from number to number. It's actually a big change as we go from number to number. Pure water, H2O, an OH and an H, has a pH of 7 because we have an equal amount of H and OH. Our pH scale goes from 0 to 14. The lower the number, so as we go from 7 and our number drops down, that is something that is more acidic. A lemon juice, stomach acid, things like that, around a pH of 2. The higher the number, the less acidic or more basic it is. Ammonia, baking soda, pH of 9.5. Seawater, pH of 8. Blood, its pH is 7.4, so it's just slightly basic. Note that there's another word here, the alkalinity. So alkaline is just another term for base or basic. So you'll just have to kind of equate that in your head, that there's another word to make sure that you understand. You've heard of alkaline batteries. So alkaline, basic, those are the hydrogen acceptors. One way to remember this, if we go from 0 to 14, that our low numbers are A, and from 7 to 14, B, acid, base. It also works acid, alkaline. It's in alphabetical order. So if you're like, man, I can't remember that a low number below 7 is an acid, use that alphabetic order to help you out. And then there's something called a buffer, and a buffer is something that is not a strong acid or base. It's a weak acid or base, and it is going to be able to accept some of those hydrogen or hydroxyl ions in a solution. So if like we talked about temperature before, right? If you go out into 120 degrees, you don't instantly jump to that temperature. A buffer is something that accepts. So if you drink, you wouldn't drink straight lemon juice, but if you drank water with lemon juice in it or water with vinegar in it as a health benefit, it's not going to immediately change your pH because you have these buffers in place to kind of balance that out a little bit and accept that shift without swinging wildly and affecting your blood pH wildly. So buffers are there as kind of a cushion. I also like to think visually, if you've ever gone bowling and you've had those little the things that they put in the gutters and it blocks it. So a buffer is kind of like that. It gives you room, like you can stay in the lane because the buffer is there serving as your protector for those gutters. If your pH, for instance, gets into the gutter, you could die. It's very serious. So the buffers are there to give you a little extra wiggle room so that you don't instantly go, whoops, okay, too acidic, whoops, too basic, you're dead. Buffers are very important. This will come back a lot as we get deeper into really into the second half of our 2-semester A&P course. All right, so that is what I wanted to go over. We talked about water, we talked about salt, and we talked about pH. Again, if you have questions on this stuff, guys, just reach out, let me know. I'm here to explain it to you and happy to do that anytime you need.